This tutorial presents a user authentication solution targeting IoT applications for smart devices. In the introduction tutorial, it was discussed that most users prefer password-less login. Hold and tap is a novel scheme offering password-less login. This research work is a part of my Ph.D. dissertation titled, Next-Generation User Authentication Schemes for IoT Application. Also, we published in a paper titled, Risk-Driven One-Shot-cum-Continuous Behavioral Biometric-based User Authentication Scheme for Smart Devices. Hold and tap is a risk-driven one-shot-cum-continuous behavioral biometric-based user authentication scheme. The scheme exploits two natural users' behaviors to authenticate them while they access IoT applications on their smart devices. The first behavioral modality is touchstrokes to enter any random 8-digit number. And, the second behavioral modality is hand movements holding the smart device, during sign-in activity. Also, the scheme deployed a simplistic risk assessment model that continuously monitors the need for re-authentication. We considered physical attacks, where the adversary accidentally finds an unlocked smart device. The adversary is a friend or colleague who possibly knowing users' PIN or passwords, and the adversary records users while they interact with their smart devices. Eventually, the adversary exploits the weaknesses of knowledge-based authentication schemes to gain access to the system. Now, let's understand the working of hold and tap. Typically, the life cycle of an IoT application starts with the sign-in process and ends with sign-off. To authenticate users, our scheme can be simply stitched to existing login mechanisms as a hidden security layer. To enhance their usability and security. That is, users do not require to remember their PINs or passwords, and authentication decision is not simply a binary comparison. After the successful sign-in, the scheme continuously monitors client attributes and computes the risk score at the instant users initiate critical activities. Based on the risk score, it permits users to perform that activity, otherwise, scheme prompts for re-authentication. If the risk score is higher than the threshold. Thus, the scheme omits the need for token-based second-factor authentication at the time of every critical activity. Some of the related works are: Jung proposed an authentication mechanism based on tapping. They collected tapping data from 80 users. And their system achieved high accuracy with averaged 3.65% EER. Luca proposed a touch-based scheme that leverages different touch features like X and Y coordinates, touch pressure, touch size and the time offset, generated from different slide operations to identify a user. They achieved 77% accuracy on a dataset of 48 users. Feng presented a finger gesture-based authentication system called it FAST. The system extracted 53 touch features and achieved a FAR of 4.66% and FFR of 0.13% on a dataset of 40 users using gesture sequence-based authentication. She presented a multi-sensor-based approach that incorporates the accelerometer, touch screen, voice and location data to passively identify a real user. They achieved 97% TPR on a dataset of 7 users. Li proposed finger movements and a touch-based authentication system that uses accelerometer, orientation, compass, and touch sensors. They reported the 95.78% accuracy on a database of 75 users. And HMOG that utilized hand movement, orientation, and grasp behavior reported EER of 7.16% and 10.05% for walking and sitting posture, respectively. We evaluated our scheme on a comparatively larger dataset of 95 users collected in the wild. We evaluated our scheme for sitting, standing and walking posture. Also, we introduced a risk assessment that does continuous user authentication throughout the user session. To design the hold and tap user authentication scheme, we prototyped an Android application that replicates a banking system to collect users' touch strokes and hand movements data. For collecting these two behavioral modalities, we used existing sensors present in the smart devices. We collaborated with Uber Testers, a crowdsourcing testing platform. The experiment was run over 3 days with 1 session per day. 95 users were qualified for this experiment, in which 75 were males and 20 were females. 89 right-handed and 6 left-handed, with 90 people in the age group of 20 to 40 and 5 in 40+. Overall, we collected 11,400 samples. With 2,085 samples in 3 different postures: sitting, standing, and walking. During the testing, we asked users to use any of the 3 postures and collected 2,085 samples. We also performed a system usability scale survey to evaluate the usability of hold and tap. To collect touch stroke data, we used in-built touch sensors. We extracted 30 features from the 8 touches by users to enter 8 random numbers on the touchscreen. Here in the slide, you can observe. We computed 8 features type 0 based on dwell time. Dwell time is the timing difference between the release and press of the same key touch. 22 features of type 1 to type 4 based on flight time. Flight time is the timing difference between the press and the release of successive key touches. Interested viewers can refer to our papers for more details on touch stroke feature extraction. To collected hand movements behavior, we used 5 inbuilt sensors that are: accelerometer, gravity sensor, gyroscope, magnetometer, and orientation sensor. And 2 sensors we derived from accelerometer, gravity sensor are high-pass sensor, and low-pass sensor. From each of these sensors, we get 3 raw streams X, Y and Z to determine user identification signature. Generated in 3-dimensional space due to hand movement while they sign to our prototype application. Afterward, we computed 4 statistical features from these raw data streams, which are mean, standard deviation, skewness, and kurtosis. You can observe in the slide, for each stream we get 4 features. Total of 16 features per sensor. And, there were 7 sensors, so in total, we get 7 multiplied by 16, which is equal to 112 features. We used feature-level fusion. After combing both features 30 from touch stroke timings and 112 from hand movements, we get a total of 142 features. For feature selection, information gain attribute evaluator provides by the Weka tool. We selected the top 66% of 142, that is 93 features, to design the classification model. This threshold we get dividing the number of users by the number of combined features. Feature selection helps to determine the most productive feature subset. With the smaller feature vector, the classification model incurs smaller computational time and fewer memory requirements. Before moving to the classification model design, let's see the design and working of the hold and tap risk assessment model. According to ISO 9000, the risk is the effect of uncertainty on objectives, and an effect can be a positive or negative deviation from what is expected. An objective can be strategic, tactical, or operational. To design a risk assessment model, we determine client attributes that can characterize a user session. For this purpose, we use historical and contextual attributes such as transaction pattern, user's geographic location, access time, IP address, IMEI number and MAC of IoT endpoints. The first step involves assigning weight to each client attribute as per their importance. Then, for a new user session, the occurrence of each client attribute value is compared with the previous N1 session. Next, the frequency of occurrence is computed using the formula client attribute value divided by n-1 as shown in the slide. Frequency of occurrence tends to 1 indicates lower risk and the frequency of occurrence tends to 0 indicates higher risk. Afterward, we compute the frequency of non-occurrence using the formula 1 minus frequency of occurrence. Frequency of non-occurrence tends to 0 indicates lower risk and the frequency of non-occurrence tends to 1 indicates higher risk. Then, we compute the impact of non-occurrence as a product of frequency of non-occurrence and their client attribute weight. To compute risk score, a cumulative impact of non-occurrence associated with each client attribute is calculated using the formula as shown in the slide. Our risk assessment model is simple and easy to implement. We designed a multi-class classification model for a dataset of 95 users. We utilized the MATLAB PR Tools toolbox and used naive Bayes, neural net, and random forest classifier. In the slide, you can observe a random forest classifier gives the best true acceptance rate of 96% for the false acceptance rate of 0.01%. With 15 training samples by using the selected feature set. We also performed the security analysis and found hold and tap as 100% robust against random attack. And against mimic attack, the robustness was 98.75%. For usability analysis, we conducted the SUS survey. System Usability Scale is a standard tool widely used to record user impressions about the usability of a system. A mean SUS score of 68 or higher is considered better with a higher probability of wide user acceptance. For hold and tap, we got a score of 73. If you have any questions regarding hold and tap, please write the comment. Thank you for watching the video. Please subscribe to my channel and like the video.